Another draft physics video presentation. Nick Sirius, something like that. Nick something. Whatever this is, Science Asylum, right? Okay, so I probably played this video in the past, but since I've upped the game in the last month or so in terms of getting a lot of this photon stuff a lot better defined. It's worth going over this history. So anyway, so he does a video, what the heck is a photon? As if he's going to provide some sort of rational answer, and he really doesn't. And he's certainly not going to explain anything like the context of the history or the comparison between the ideas that were available. And so you can always equate sort of these things to the one of like the biggest mistakes in physics, and made by Benjamin Franklin. Very good little scientist and all that kind of crap. Really smart guy, and completely understandable mistake. I mean, I had a choice which one to label, plus and minus, like up, down, and because there was no information about which one was right, he sort of just guessed, and the guess was wrong. He had a 50-50 chance, and he got it wrong. Which one was all he knew is the difference, glass half empty, glass half full, sort of thing. He knew there was a difference between the two things, and one had to be too much and one had to be too little, and they just got it wrong. And physics never fixed it. At least they concede it's wrong, but they never fixed it. But these are the kind of mistakes that were common. You could make these kind of mistakes, and if you were rushing to judgment, that's what you do. You make mistakes like that. Science is supposed to be a little more careful, not make those kind of mistakes. Blah 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 blah. So this whole argument about what a photon is really just has to do about these two theories, right? I mean, whether it's a wave or whether it's a ray of something. Whether you call them particles versus fields, I don't know, some kind of crap like that. And then it really got messy. Okay, you had those two simple kind of things to argue about, and Newton was on the side of rays because shadows, waves would go around things, and it didn't look like in most cases there was much going around. A little bit, but not much. And therefore particles made more sense than this idea of a continuous wave, and the idea that photons seemed discrete. They seemed small. They landed in little tiny locations. And that sort of was becoming something that could be argued. That you could make a small path, and the thing was small enough to get through the small path. The photon wasn't something that was flying through space and all kinds of places. It was a small bit of energy, not a big, giant, continuous, huge thing of energy. But obviously you could have a lot of rays, and that could look like a wave. So anyway, so there's some reason to get it wrong. There's some reason to not have a conclusive answer. And I guess I would argue now there's a lot less reason, because there's a lot more experiments that kind of point out that, it can't be one, it has to be the other. And so then they settled on this wave-particle duality and all that kind of stuff. But again, he titles the video as if he's going to answer this question. He didn't come close to an answer, just gives us the line. He gives us the rationale for the positive being in the wrong place, in my opinion. So, I've sort of thrown this context in. I mean, to me, a photon always was a ray. I mean, even when they were teaching me it was something else, I was like, sorry, that doesn't make any sense. And clearly the way they describe the wave, waves have two features, and they were blending the two features. So you could argue, you could say, I guess we should do that, that you have two ideas of what a wave is. A wave is like this thing, waves in water that could be, this could be a mile of distance, and this is a wave. And then they draw it like, well, no, this is a photon wave. Somehow it's this small thing, okay, and it's supposed to have these two fields in it, and it's traveling through space. And those two didn't really match, because that's really saying that your photon is doing this, right? I mean, that's what it's saying. It's saying there's a ray that's waving. So then they turned it into this waving ray, which is even less likely, in my opinion, to be the truth. So anyway, so from, when they drew that thing, my brain just said, no, these are clumps of stuff, and you're just shooting them in a ray, and then, the sort of fit with the whole idea that, you hear a frog can see this, and we can only see, 6 of these things, but a frog can see 3 of these things. That's irritating. Glare. Anyway, so that sort of tells you that this has got to be some kind of clumpy thing. It's measuring the clumps, and, depending on what kind of sensitivity you have and the device you're measuring the photon with will tell you whether it's a photon or not, right? This is a photon, this isn't a photon. Well, unless, of course, you're a frog, then this is a photon, too. So what, the universe has more stuff in it based on whether you're a frog or a human? I mean, obviously it's the same thing. It's just in a form that, you can detect or we can't detect, but it's still doing whatever it's doing. So then the argument would be is whether this is okay, so we put these clumps right next to each other. Well, and then we say the wavelength is the size of the clump. Well, then, you're into the radio waves are a mile across, so you're saying this is a mile big clump of something, and it's got a polarization of 1 mile. It's a gigantic big bubble of something. That doesn't really wash. So then it becomes, more rational to say that what you're really measuring is the space. The wavelength is just the space between something that's very small and very discrete. So this is your wavelength. You got a bunch of nothing, nothing, nothing in between something, something, and something. And so it's a stream of bullets. And then you have to say, well, what's polarization then? So it took me a while. It took me a lot longer, in hindsight. It's like, geez, how did you figure this one out? So polarization then becomes an issue, and you say, well, what's it just seemed, like I said, I didn't really catch on that polarization just means they're a little bit, they're still parallel to each other, they're still moving parallel, but they're out of alignment a little bit, so that's your polarization, and it's really just dependent on the speed of light. The speed of light dictates, how often something's happening, but it also dictates when it's happening on a surface. You can sort of understand that if a surface is being agitated by electricity, that it could create photons in a sequence. As the electricity passes, one goes up, and then a little bit of time passes, another one leaves, then another one leaves, and then another one leaves, and that they would be in an arrangement. So it wouldn't even be random. You could almost argue that the polarization really is just saying that they're in a spatial relationship distance-wise this way that's proportional to the distance this way, because they're both based on essentially the speed of light. So the geometry makes sense that you have a little bit of a change in the trajectory. Okay, it's all going the same basic way, but there's a change in the trajectory based on the fact that this really is an antenna. All right, light, like all the other radio waves, like the rest of the stuff in the spectrum, is basically being produced by an antenna, an atomic antenna. And so, yes, radio waves need big antenna. Higher the frequency, the smaller the antenna you need. Smaller amount of matter, smaller number of atoms that produce the sequence of bits of energy. So anyway, that's sort of a history that I think, it's always got to be part of the context. So, to me, like I said, I have an intuitive bias, no doubt about it, in the sense that it never, the idea of two fields, whatever they are, right, this electrical field and a magnetic field, somehow oscillating in space, whatever the hell that would mean, and somehow these fields are oscillating in just this location, and the field oscillation is traveling through some vector. Well, sorry, that just sounds like a bunch of complicated mush. Why would the universe do it that way? Where would it get all these tools to make all these, all of that complexity when the simple truth is I could think of it just like bullets, and I could think of firing a gun in a certain rate, and I could say that if I'm moving as I'm firing the gun a little bit, there, photon, made one. And so obviously a photon, by strict definition, I mean, come on, people. I mean, see, this keeps coming up in comments. Like, people don't understand. Photon. It has to be a composite. Obviously, the difference between what we see and what the frog sees is because it's a composite particle. It's not a particle. It's not a ton. So they made a mistake. They shouldn't have called it a photon unless they were calling this little quanta a photon, this little bit a photon. That would have made sense. Maybe Einstein was doing that. But regardless, this is what it got called. Like, a photon is the entire package of energy. And obviously we don't have a consistent definition for the entire package. The entire package can be 3, for a photomultiplier. But the package called photon needs to have 6 to be array length. And they never talk about this length thing. How many lumps in the wave you need before you have a photon. They never talk about it. It's kind of a fundamental, elemental part of this discussion. And the fact that they don't talk about it is just part of the evidence that their theory is a little mushy and messy and it doesn't quite work. And so they don't talk about the parts that don't work very well, that don't make much sense based on their theory. That's probably enough of a context. So, I don't know, I mean, I shouldn't have to restate this over and over and over again and be explicit about what a photon is, okay? The individual bits are flying through space, right? And they're at a specific distance. So the distance between them is one feature. The height, okay, the amount they're out of alignment, is another feature, polarization. And they're all just moving through space like that. That's what I'm arguing. This is not a photon. It's something. It's the composite that makes a photon. It's a piece of, you can call it a faux something, whatever. I say force bit, I say, quanton, doesn't matter. But the point is a photon is not this thing by common vocabulary. And if it was, it would make more sense. The whole conversation maybe would make more sense if we understood that photon doesn't add up to what we see. You can't really. The word's just so fundamentally broken now that the concept needs to be re-understood. That a photon is made of elements. Elementons, So anyway, that's the best I can do. So we'll play this video that doesn't say anything. Frankly, in my opinion, doesn't say anything useful. I guess you might as well just do this picture thing. Oh, well, let me read what he says here. A photon is a purely quantum mechanical object. So says them. All right, I don't think they have any. There's no reason to think it's a woo particle, frankly. Representing the smallest piece of energy, while containing, just like gravity and just like magnetism and all the other things, it contains energy. It can manifest as energy. It has substance that is conveyed at the speed of light, if that's the way you want to say it. So like all the other forces that move the speed of light, that's what it does. So it's really the speed of force. So light is a force, would have been a nice thing for him to say here. Are quanta for light. So the smallest piece of energy are quanta for light. It represents the smallest piece of energy for light. That doesn't even make sense. Every quantum particle is a packet of energy. Well, that's sort of redundant. So this is the problem, right? It's made of quanta, is what he should have said. The photon itself is not a quantum mechanical object. The little bit is a quantum mechanical object, if you want to say it that way. Is the packet of energy. So how do we tell photons apart from electrons, quarks, and neutrinos? Well, he certainly doesn't do that either. And I would argue that often you don't tell them apart. That's why you've invented 4,400,000 and some extra particles and a bunch of antiparticles. It's because you really can't tell the difference between forces and particles very well. You haven't been able to do it yet very well. Okay. So this should be sped up, and so it won't be quite as long as the usual.
A lot of you feel like you know what a photon is. It's just a packet of energy or whatever. But you know what happens when you assume. You make a mistake.
So he's joking about something really fundamental as a problem in physics, is this idea of making a mistake. And they've done that. They've made mistakes. And he's sitting there joking about it like, oh, you know, that's something you do. Physics doesn't do that. And I would argue that you can look back into the history where this was established. It was established in an environment of some ignorance, like some sort of UFO thing of the 50s, you know, where you had fuzzy technology, and, you know, you could look at a fuzzy image and maybe you could be fooled into thinking there were UFOs and all that crap. Maybe you could believe some of these wacky stories people could tell. But we're not there anymore. And physics ought to grow up and admit that it's got some foundational errors that need to be fixed. But there's no sign of any will to accept they've made some mistakes.
Sometimes. Calling a photon a packet of energy isn't wrong.
It's too loud now. I always have to, fiddle with this stuff. Yeah. Sorry. Where's the play button?
It's just not very useful because everything is a packet of energy. I have some...
So again, this everything's a packet of energy isn't really true. Something has to be moving. And the point is I would argue, is that forces, things like light with little bits of energy that are always moving the speed of light and never stop, interact with matter and push it around. So if matter's moving, if my finger's moving, it's moving because there's a bunch of forces that are being manipulated, okay, in creating, energy going this way is being converted into energy going this way, through a process of, how this stuff bounces off protons and electrons. And so if matter's moving, it's moving because forces are being applied to it. That little quanta is being shot at it. There's actually little rays of photon, you could argue, photon-like energy, just like a photon, right? Radio and microwave and gamma and even electricity is moving through my finger, shooting around to make it do this, okay? It flies through my arm even, it does through all kinds of stuff, and it makes this happen. Okay, a little electric impulse hits another pile of little atoms. Those atoms shoot a little bit of rays at something else. Those rays make that, and that's how this is happening. But it's happening because matter is being forced to move. Electrons and protons don't move because they say, I'm going to move somewhere. They move because the little quanta, the rays of light, little bits of bullets, are pushing them.
In this box. Can you guess what it is? No? Here's a hint. It's a collection of atoms. Did that help? Probably not. Surprise! It's a squirrel. My point...
Oh, yeah. No, there's no point. My point is let's do science like Barney the Dinosaur science or something. And get 500,000 views for this crap.
There's a better way to describe photons. Yes, it's a packet of energy, but it's the details about that energy that make it a photon.
Yes, says you. I mean, I'd say that statement is true. Details matter, but you don't have any of those right. And you're still talking some archaic notions made up, in 1801 or, going all the way back to Huygens. So you go all the way back to 76. You made mistakes and you just haven't fixed any of them.
How should we tackle this? I think the top-down approach is going to work best. Reductionism. Basically, it's the idea of starting with something normal-sized and then breaking it up until you find its smallest pieces.
Well, this is hilarious. Yeah, duh. Yeah, and the whole point is they've been doing this reductionism since the 1600s, when the debates sort of started about ray versus wave, and you've decided it's a wave, in spite of the fact that you have all of this experimental evidence that tells you it really can't be a wave.
You might call it elementary pieces. Honestly, this is how we came up with quantum physics in the first place, so it seems...
Yeah, well, you came up with it because there was a void and you filled it. And you filled it with a bad, kind of a reckless and sloppy decision that based on tiny bits of evidence that you quote mined out of the field of evidence, and you said, okay, we're going to play this, we're going to say something like wave-particle duality when we don't even believe that. We really are all wave ether people, and you just won't say those words.
Seems like a great place to start. Elementary particles are like bite-sized pieces of something ordinary. Kind of like how this video series comes in bite-sized pieces.
Elementary particles are bite-sized pieces. I mean, it just doesn't make any sense. Elementary particles are two kinds of things. They're either the force bits or they're the matter bits. So, I mean, if this could make sense if you just say, okay, there's two kinds of stuff. There's the stuff moving the speed of light, that's this little quanta stuff. And then there's stuff like electrons and protons that are bigger and heavier and realer, and they don't do any of that crap until some force acts on them. I mean, what is wrong with that simple description? Oh, that's right, nothing. That would be the right answer. That's what the right answer looks like.
This is quantum physics. It's almost like I planned this or something. Anyway, a photon is the smallest piece of light, like you might find coming out of a flashlight, like this. Can I...
Right, the smallest piece of light coming out of a flashlight like this, which is making gazillions of photons, right? So you're going to describe the smallest, you're going to describe its elemental function by showing it in a world of billions and billions and trillions of them.
A flashlight? Do you remember what happened the last time I gave a flashlight to a clone? I wonder what this button does. Oh, turn it off, turn it off!
This joke doesn't even make sense. He pointed a flashlight at him.
Behave. What if I promise to behave? All right, we'll try this one more time. Okay, back to business.
God. People's sense of humor, I mean, it's just completely subjective, I guess, right? I mean, some things are funny to people. I don't get it.
A beam of light is one of those normal sized things I was talking about earlier.
Alright, a beam of light is a normal size thing. I mean, so again, it's a beam, so it's made out of something, and that isn't normal size. It's the smallest shit in the universe. And yes, you are putting it at a frequency, so therefore. But it's funny how he says a beam of light when they don't believe in beams.
It's something we can see with our eyes, something the size of us. But if we're going to understand it like a quantum physicist, we need to break it into smaller and smaller parts until we find something we can't break anymore. Light beams are giant collections of many electromagnetic waves.
Alright, so whatever, see, they just jump. Whoa. Okay, so this is the elemental, is drawing this thing, whatever this is. Again, this electric field is somehow doing snaky stuff, and then there's some sort of magnetic field doing some sort of snaky crap, and it's somehow in a location, and yet we're supposed to understand that as a wave because it has these lumps in it, even though it's nothing like a wave in the sense it doesn't look like water waves, it doesn't look like an ocean, doesn't do this. So whatever this is,
If we focus on one of those waves, we can see a repeating pattern. One cycle of that pattern looks like this. That's one wavelength of that wave.
Yes, and if they just drew a bullet, they could just draw a bullet going through the screen and just say the distance between the bullets is a wavelength,
There really isn't anything smaller than this for a wave.
Well, and again, they won't talk about polarization here. You won't talk about how big this thing is in space.
Is that what a photon is then? No. We have a slight problem. Light waves can be anywhere on the EM spectrum, including the low frequency end like radio waves.
Right, and they probably even shouldn't say that, right? There should be a word for light, which means the stuff we can see, and that ought to have a word, and then we ought to have a separate word for all the other stuff. And so I guess photons would be a better way to say it, but yes, it's a spectrum of photons. spectrum of frequencies. And this is one type of radiation. But they call it electromagnetic spectrum. It's really the photonic spectrum. Yeah. A force frequency spectrum.
A single radio wavelength can be as large as a small city.
I mean, that universalizes everything. I'm just saying, see, if their terminology was a little better, if they said speed of force, you know, because all the forces go the same speed instead of speed of light, you know, which makes light different somehow, then maybe all this would be understandable, and they'd understand that the same force that makes gravity and all the other stuff is really the same force, and you're just saying that when the force is at a specific frequency, it can do specific things to specific electrons. And that's all there is how you affect matter. And you can affect matter different with different frequencies. Different matter is subject to being tipped by a different frequency.
I find it hard to believe that a single photon could ever be that big. Maybe we're looking...
Yes, so at least he got that part right. I find that hard to believe also. So really the bigness is just about the distance. So I can shoot bullets really slow, and they can be a mile between the bullets. But they're going the speed of light, so yes, that kind of fixes the problem.
Looking at this all wrong. I seem to remember saying something important earlier. Yes, it's a packet of energy, but it's the details about that energy that make...
So a packet of energy, and so this is where they're just going to make it all confusing, right? Because what does this packet of energy mean? It's a packet of energy at a frequency, or it's a bunch of energy inside the, you know, which one's the packet and which one is the stuff. And so this is where all the confusion is, right? Because this is the photon. Oh, well, no, the packet is the photon. I mean, which one is which? So it's all this confused language that just makes a mess out of this, when it's clearly, photons are clearly made up of something more elemental. So photon is not elemental. Photon is composite, and the elemental energy, the quanta, the bits of force, are the photon. And again, even if you want to believe it's a lumpy wave thing, you've got to understand the wave has nodes, that there's a certain length of wave that matters. So obviously the wave has to be understood as elements inside the wave. The elements of the wave are the photon. When you add up the elements, you get a photon. You don't get an elemental photon. The photon is a length of waves, if that's what you have to say.
Make it a photon. Right. This isn't about the space something takes up. Elementary particle...
Well, it really is about the space things take up, but whatever.
Like photons don't really have any size anyway. This is about...
So again, that's kind of a silly thing to say, right? Photons don't have any size anyway. When we know the thing we're calling a photon, which is a collection of these elements, we know that takes up space because of polarization. So we know at least the polarization takes up space. And you don't have to be very smart to figure out that the length of the ray takes up space. That, you know, to have your wave nodes, that takes up space. The photon must travel through that space, occupying that space. The radio wave occupies miles and miles of space to be a thing that can actually cause an effect.
Energy. It's the energy we have to break into pieces.
Well, here we go. Now we might get closer to the truth.
Let's start with a standard incandescent light bulb. This one is 60 watts.
This won't help you, though. Okay, having the mathematical formula doesn't explain the energy at all.
Means it transforms 60 joules of electrical energy into heat and light every second.
Right, into heat and light. And again, the argument almost is that somehow this heat stuff isn't sometimes the same as the photon stuff, when of course we know that it is. Some of the heat is radiated as this very thing called a photon. It's just one that we can't see. An infrared photon or a radio photon. Some other photon, a microwave photon. Lots of different kinds of photons are coming off the light bulb, not just visible light ones. So to call all the other photons heat is kind of cheating those photons, because they do have a frequency. Now it also creates heat, which is just noise. That is no frequency, no pattern. just a bunch of arrangement of little bits that are exciting the metal and causing it to move and vibrate. So it's also creating electricity and magnetism and all kinds of other force elements. And I would argue gravity.
Incandescent bulbs are terribly inefficient though, so only about 10% of that actually becomes light. When you turn it on, 6 joules of light leave the bulb every second.
So we know that 6 joules of light, he's saying, right? But there's no visible light, is what he should say. There's lots of joules of other kinds of at a frequency rays coming off the light bulb. So it's producing lots more than 6 joules of light. Just happens to be the photons we can't see.
But that spreads out in all possible directions. Eventually, we're going to...
And it spreads out, not on, like, so again, he just says the words spreads out. Like, somehow the energy is going to all these different locations when what's really happening is there's a clump of atoms, okay, a collection of atoms. You could almost think of the atoms as being something that can bulge this way or it can bulge this way. So it's, I can pop this way, I can pop that way, I can pop this way, I can pop that way. And, you know, that's basically what's going to, you know, cause this thing called the photon. Is going to be a bulging one way or bulging the other way and shooting these little bullets into space at the right frequency. And so that's what's happening to the matter. The matter has a matrix. The matrix of the matter moves in a certain way that causes this effect of creating a clumping. So when this thing's going, when you could sort of understand there's a force coming at this thing, right, from the field, energy. You can sort of understand when it's bulging this way, it's not reflecting any of this. And when it goes blow this way, okay, then obviously now it's going into the force, it's reflecting a lot of this stuff. And so that's essentially the creation of your photon. You know, so but that's what sort of has to be understood, is there's a lot of energy that goes in that just causes blah, 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 ripples and bumps. But it doesn't create this effect where the matter itself, the crystals, blunk, you know, where they change all at once in sequence. When they move the energy, the little bits of hidden energy, it's like the crowd getting pushed towards a door, and there's like one fat guy, you know, like say you have a bunch of people and they're kind of trapped in this doorway, and you're pushing more people through, and finally you push the fat guy through, and then everything just flies out at once. It's almost like that could be the argument. It's a pressure argument, and all of a sudden the matter yields to the pressure and the atoms all turn, and then they get bombarded from the other direction. They feel the pressure, and then all of a sudden they all turn and flip. So there's a dynamic that's creating the photon. But the photon is again, see, he's trying to say, well, the light bulb is, that's what I was supposed to be talking about. So he gives you this idea that the light is coming out of the light bulb. Alright. In waves, you know, like this. When, no, the argument is each little piece of atom on the filament, each atom, you know, each crystal, each group of atoms on the surface is engaged in this getting jiggled thing, okay, and they do something collectively is when you see an effect. And so there's a ray coming off of this little piece of atom, and a ray coming off of this one, and a ray coming off of this one. The rays are going in all directions. The rays are going in all directions. There's no wave going in all directions. All these waves are going, all these rays are going in different directions. They all happen because of the way the energy is coming in. They're all happening in the same phase. So they're all shooting out into space. You know, the guns are shooting all these directions at once. Different guns are firing. And all the guns are firing essentially on the same trigger. The same, you know, you have a bunch of people with their finger halfway on the trigger, and you hit the persons, you know, and one person hits the other person, they all hit each other, and they all shoot the gun at the same time. So the bullets are all going out in different directions, because there's a lot of different guns, different atoms, and so that's the photon. So it can look like a wave, but it's not a wave in the sense that it wasn't made by any traditional way of a medium causing a wave. The medium has nothing to do with it. The wave is just a byproduct of how the atoms produce the photon rays. A perfectly viable explanation that they'll never consider. Well, I'm going to try to force them to consider it.
See gaps between those pieces. Those tiny little pieces of light energy are called photons, but the amount...
See, so he said the tiny pieces are called photons. They really can't be. You can't have the same word for two different things. The ray can't be called a photon, and then you can't call the individual things. It's like calling wheel, and then calling a group of wheels wheel. It just doesn't make any sense. You can't do that.
The amount of energy they have is very small. You can calculate it using E equals hf. The h is Planck's constant.
Okay, so this is a whole nother perversion again. So he didn't get elemental again, because now he's thinking the frequency means something to the quanta. And the whole point of quantum mechanics, the whole point of it, its origin, was sort of understanding that the whole Planck constant is a way of understanding that the thing that's elemental, okay, that has this you know, you can't cut it into anything smaller, the H part there, the Planckness, is the fact that the quanta itself, the substance that makes the photon, that is always the same. And what you just do is you change how close they are to each other. You know, you make them closer in space, that means more of them fit in the space, and that means there's more energy in the space. So, you know, this space only has 4 Q. This one has 8 or 9, 8Q, right? In the same space. So yeah, this one has more energy, but it's not more energy because these things are more energetic. And it's also not that frequency does, there's no equal sign between energy equals frequency. So even if you don't need the constant. I mean, just take the constant out. They're basically saying energy equals frequency. It doesn't. Frequency can have that effect, but in every circumstance, frequency doesn't mean more energy. Because say if you have a collection of quanta and you only have 100 of them, it really doesn't matter whether you send 100 at this high frequency or send it at this lower frequency, except that that's the time. The amount of time you're going to, it's like a dam breaking. Well, the dam is the same amount of water that you could run down the stream in an hour, and it wouldn't cause any harm at all. But if you put all that water in 1 minute or 1 second, well, then it can do lots of harm. But it's just circumstantial. It doesn't mean the little pieces of water have more energy, so that's what's so wrong about this. The pieces of energy, in an infrared photon have the same amount of power as the energy in the gamma ray, and the only difference is the frequency. But the frequency doesn't make it more energetic, doesn't make the quanta more. And that was the whole point of the Einstein photoelectric effect, is the whole idea of understanding the quanta doesn't change. Well, anyway, this is just one of these glaring mistakes. They should have never made an equivalency between energy and frequency, because it only matters to electrons bound in atoms. That's the only place frequency matters. Every other place you interact, every other way to interact, frequency wouldn't be relevant. It would just be how many times did you hit me. So if there was a free electron couldn't care less about this stupid frequency crap.
Which is extremely small. The F is frequency, which tells you what type of light it is, and in the visible range, it tells you color. So the energy of a photon is a constant times its color. For that 60-watt light bulb, that's 10 million trillion photons per second. Woo! That's a lot of photons!
Yeah, obviously, it's a lot of photons. It's a lot of rays of light.
Individual photons don't have that much energy, you have to get really far away to notice the gaps between them. Let's say you move away from the sun at an unimaginable speed, and somehow manage to avoid any of Einstein's relativity. Eventually, way out in space, you'll start to notice the sun's light flicker. What you're seeing are individual photons. Actually, the human optic nerve doesn't send a signal to the brain unless 9 photons arrive within 100 milliseconds.
So he says 9 photons. So what is he talking about again? Is he talking about the quanta, or is he talking about the whole package? So again, just useless mush. And he says 9, I've heard 6. But clearly they don't talk about this 9 thing. They don't talk about this length thing at all.
You have to ruin everything, don't you? I don't ruin things. I make them more accurate. All right.
So the flickering part just has to do with as you get far enough away from something, all you're getting is one little tiny ray at a time. So, you get far enough away, the light is all spreading from point sources, so it's the photons are getting fewer and fewer and fewer because they're spreading and spreading and spreading. So you might get one, and then a minute later you might get another ray will hit you, but you're just getting so far away that you're seeing the individual rays. So there's a trillion of them at the source, the light bulb. But by the time I get a certain distance away, it ain't a trillion anymore. And then it's a lot less than a trillion, a lot less. And I start seeing the division between the rays, where I can't see them when I'm up close.
So humans can't see individual photons, but that actually explains a few things. If you move away...
See, so again, humans can't see individual photons. Yeah, they can. They can't see individual quanta. Nothing can. Nothing can see one quanta. Nothing can measure it. There's no device that can measure it, because the only device could measure it would be a device that was made of one quanta. And there's no such device.
From the sun, like we did earlier, you can't see the flicker of the photons. So at about 750 light years, the sun's light will just fade away into the blackness of space. That's why the night sky is mostly black, lit by just a few nearby stars. The rest of the photons are just too infrequent for us to see.
So that's not true. It's just that, obviously by distance, the further away you get, the farther away you get, the photons are being degraded through the entire path, and they're hugely degraded getting to our eye. Just the substance of our eye is tough on a photon, in terms of it has to go through membranes, it has to go through lots of transparent mediums, and those transparent mediums, to get to us, it's going through the atmosphere, going through this, going through glass, going through whatever it has to go through, is too arduous for the photons.
What the heck is a photon? Right. Stay focused, Nick.
They're always breaking and remaking would be the simple. The argument I would give you is the cause is the fact that this should always have been understood to be just a collection of bullets that are flying through the air, little dots. And whatever they hit, the dots get messed up, the dots get sent to new places, go in different directions, and you're just remaking a photon constantly out of the pieces. So 10 photons worth of quanta, so that would be maybe 1,000 quanta, go into a circumstance, and atoms, and only 800 are remade. So it's just, you just keep degrading the light as it travels through space. Through space that always has some matter in it. And the matter just keeps taking pieces off of photons.
There are a lot of little packets of energy floating around in the universe. What makes them photons is all in the details, my dear crazies. Photons have a specific set of properties that make them photons. A charge...
So that doesn't say anything, right? So this silly stuff, a charge equals 0, that's a force. Okay, it can't be a charge. Okay, it's a force. Forces cause the phenomenon of charge by them being the proton and the electron acting inversely to a force. So however you want to think about it, but that's the obvious thing that protons and electrons do, is they act inversely to the same condition. So I can throw the same force at them, and one will run away from it and the other one will run towards it. So however you want to interpret that. I interpret that to being there's two forces, okay, and that's really and they inversely react to the two forces, and that sort of explains everything.
0, a spin of 1 with 2 possible...
So more nonsense. So like there's some evidence of a photon spinning, that there's any difference between photon A and photon B except for its polarization. So they got all this spin crap doing polarization experiments, and so it doesn't really have anything to do with spin. It's a fake word, and they'll concede it's a fake word. and it's for a quality that doesn't really exist. I mean, the photons are all the same. They're made out of the same bullets. And yes, you can have an atom that makes a photon where the electricity went this way. You can turn an antenna, right? A physical radio antenna. You can turn it this way, You can turn it this way. You can turn it this way. You can turn it lots of ways. You wouldn't call that the spin of the radio wave. I mean, it's just wrong.
Orientations, and lastly, a rest mass of 0, which...
So more nonsense talk in terms of, yeah, we know that force is created by stuff moving the speed of light. And to talk about that stuff as if it ever stops is just silly. That you ever break a quanta, that a quanta that's a piece of force that's moving in the universe ever stops. It never stops. It's never used up. It's never, it just never does. It just does one thing. It goes the speed of light, and it can stick to an electron and make it go fast for a while, but it's going to get detached by the force going the opposite way. So it just, something can share its speed, but it never stops. The force is never consumed, and that's what the universe runs on. So it's just silly to talk about a rest mass. It clearly has a mass in the sense that it's going the speed of light, and it opposes something called energy. And it's just silly to say it doesn't have any mass. It's silly.
Makes many things about photons possible. Their speed of almost 300 million meters per second, their energy being proportional to their momentum, and...
Yeah, well, you can't have any momentum when you don't have any mass. So again, that's more of this crap. So it doesn't make any sense. We'll give it a big high velocity and no mass. Well, that means you have no momentum. So you have to have some kind of mass. It's just, give it a small number mass, the Planck constant amount of mass, but it clearly has to have mass or it can't have momentum. So this is just all sort of silly. But that's part of this fix, right? P here means frequency. It doesn't mean momentum. Why would you multiply velocity times mass when velocity is c? So it's like velocity times mass. That doesn't, why would you do that?
Their inability to experience time or space.
So more nonsense. Their inability to experience, they don't experience in the first place. They're force bits. Force bits don't interact with force bits. They don't do any of that. So, but clearly they experience time in the sense that they travel a lot of distance. The same photons right now in this room have lived a 16 billion year life, or a 32, whatever the age of the universe kind of thing is. That's how long they've been alive, going and doing things. The same energy is moving all through the universe. So every bit of it, so every photon has quanta in it that has been everywhere, all kinds of places. I mean, a lot of it's been trapped in the earth, so some of the light we're seeing has been here. Some of the photons have been trapped on the surface of the earth for maybe 10,000 years. Some of them just got here from space. Some of them took billions of years to get out of the earth and got to the surface here, and are just starting to see the light, so to speak, just starting to see a hope of freedom. Some of the light here is going to go out this window and go shoot into space and never come back. It's going to go to Venus and go fly by. So it's going to go all kinds of bizarre places. I mean, that's the truth of it. I'm just saying that's more likely. I'm saying a reasonable person should be able to... This is the more likely explanation than this wooey field perturbation mush.
Packet of energy with those properties is by definition a photon.
So again, by definition a photon, when he hasn't made a distinction between the thing we see, the thing that takes 9, and the bits. The bits are the thing that takes 9.
So, got any questions? Please ask in the comments. Thanks for...
Yeah, whatever. Questions. I have critiques of what authority you have to declare these things to be true. What logic you based it on.
Liking and sharing this video. Don't forget to subscribe if you'd like to keep up with us. And from one packet of energy to another, remember, it's okay to be a little crazy.
whatever crazy means. You mean sloppy? You mean arrogant? You mean, frankly, you're not doing anything good for science with this trivial coverage, and making it all a joke. Getting it right isn't really important, as long as we have fun doing science. And fun means childish humor. Ugh, God, I hate this planet. Anyway, alright, so we'll take care of some comments. My bad, sorry, I meant to write would not start with double-slit experiment, it's a trap. Yes, well, whatever, no point. You're one of those arrogant people who just make a lot of declarations, and I don't see any reasoning behind the definition. So it's a trap. How? What, do you think they have some special wave knowledge they're going to hit me with? What's the trap? To me, it's their trap. Their trap is, why are you saying something like Huygens when you don't apply the, you call it a principle, and yet you don't apply it consistently. I've got them trapped. Anyway, Hang Draft Science, do you know what time of day? What? Do you know what time of day you are likely to live stream? Oh, no, it's not going to be. I'm not going to live stream. Because first off, the quality's worse. I can't trust my computer to do both things at once. And so, sorry, I just mean a live conversation. I'm going to actually speak to a physicist versus video exchanges or replies or whatever. I'm 5 hours ahead of your time, and I'm wondering, blah, 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 set my alarm. I mean, just to me, it's a little bit funny that, first of all, I can't stand live videos. They have so much wasted time in them. They're terrible to watch. And then the stupid chatting with chatters thing, responding to the inane comments that are even inaner, when they're streaming at 4 million comments a minute. Fuck it. I don't see the appeal at all. I so wish the video response would come back. So much more rational way to deal with subjects. Anyway, Ken has been purposely placed on social media with an objective to misinform people. So, I mean, you start off with something so conspiracy theory bullshit. No, it's obvious that there's a whole bunch of people who want to believe in woo. And so anybody who will feed the wooers, the sheeple, they just love to eat up any kind of, magical crystal Hopi bullshit. That's all there is. Make it, spiritual, shamanistic. They love that shaman kind of horse shit. So anyway, I'm not even going to bother reading the rest of that crap. Also, at dawn and dusk, the sky looks red because the sunlight passes through the atmosphere for a longer period of time. Well, you just mean it encounters more scatter. But the truth is only the blue light gets used up. So the blue light is more likely to scatter, which is the important. That's why it gets red, is because the blue light is getting scattered at a higher rate. And why does blue light scatter at a higher rate? Well, it scatters because it has a smaller polarization. So the blue light, is more likely, if it hits an electron, it's more likely to hit that electron twice, which means that any matter it hits, it's more likely to be annihilated by that matter because it doesn't have a big polarization. So it's not going to survive as well because it's going to lose more pieces. So if I have more pieces of stuff in this distance than this distance, same amount of pieces, right? So they're spread out more. Well, if I have to go through an obstacle course, obviously this photon is going to get wiped out if it hits two things, where this could survive. But anyway, I mean, if you're going to give answers, it probably should be more correct. Anyway, also the sun shines at much greater angle, therefore it passes through more particles. Well, that's basically what he already said. It's more atmosphere. The best sunsets are caused by crap in the sky. Yes, scatter is what's changing the color of the light, in the sense that you're not seeing certain colors because other colors have been eliminated. You're not seeing the color because the color has been more likely to be degraded by the process of passing through. And it's being degraded not because of what energy it has, it's being degraded because of its polarization, because it's in a smaller package. Alright, the first time I watched you, I thought, this guy fucking high. This guy's fucking high. Well, whatever. I continued watching and realized, damn, someone to take on Ken and the magnetism thing. Yeah, it's just too bad he says nothing. You know, he just talks like this language that you just can't, like, okay, it's a hyperboloid. Well, says you. Where's the evidence that anything's hyperboloiding? You know, I mean, he can say things, and you're just like, well, you don't have any experiments you're connecting that to, so why don't you show me how a magnet works by actually drawing a picture of one and explaining how it works? But he'll never do it, and he doesn't take on any of his critics, so it's, you know, it's just such a waste of time. Gravity rules all, or am I wrong? Yeah, you're sort of wrong. I mean, what rules all is the fact that electrons and protons move, and they move because of charge. So even though charge leads to gravity, okay, the charge part doesn't matter because it's as much yin as there is yang. But the point is what makes charge is what really makes gravity. So I don't know. One is the absorption of energy, and the other is the capacity to be moved by energy. So I'm just saying, from the electron's perspective, it's always charge that moves it. From the proton's perspective, it's always charge that moves it. It's not something called gravity. It's something called force. And the force has to have the polarization that's going to cause it to be affected. All right. I don't know if this is something to take apart. Just found it interesting. Well, why would I take it apart? It doesn't make an assertion, okay, about physics. Just found it interesting and topical. Maybe there's some arguments hidden in it. So this is the... I saw the video. You know, this guy's a pretty good scientist. I'm thinking he's sometimes doing pretty trivial stuff, which is sort of irritating. So it's the whole idea is...
Today on Applied Science, I'm going to show you...
It's just basically understanding that a hologram can be understood as just being like a CD or like a record. It's just playing with the fact that you can diffract light, or more precisely refract, or more precisely deflect it, so that you can make a surface that's complex, okay, and that if you shine light on that surface, the light gets trapped, certain colors get trapped, certain things will happen to the little photons as they're hitting, so the quanta is hitting lots of things, you're creating lots of different kinds of vibrations, and you can get an effect out that basically means there'll be a certain tendency for light to go this way if it's red, and a tendency for light to go this way if it's blue, or some other kind of crap like that. I mean, I don't want to get into something too complicated in its explanation. But the idea is you're just taking a consistent surface and you're making it terribly inconsistent. So it's like you could create mountains and cause effect, and then you could take the mountains and put mountains on the side of the mountains, and then you could put little mountains on the side of those mountains, and you can create a very something that'll absorb. So they actually do that. I mean, substances that are black basically because the surface not only creates traps like little lumps that could trap, but it puts lumps on the lumps, so it's really hard for, once light goes in, it's really hard for it to get the hell back out again. So once it hits a piece of the surface essentially guarantees that the light will get trapped and broken into heat, and it just be absorbed as all kinds of all the frequency will be broken out of it because of the different distances you're hitting, right? So you could sort of understand that, frequency dependency, if the little bits hit here and they're all going to hit this thing, and they hit it at different places, you can see all the frequency information is going to be lost because you're hitting it at these different reflection zones. So it's not going to reflect back all the same. So by reflecting back at different rates, you'll essentially break the frequency. So where they were lined up this way going in, they'll come out, this way, so you won't have any, you won't retain the frequency information. Well, you lost this one. I put these over here. Consistent frequency and then broken frequency. Blah, blah, blah. And so all this is really about is the holograms are all made, because there's a surface somewhere in the material that kind of carries the holographic information, and you just peel the layers off, and then you just pour your chocolate on, and you reproduce the same pattern, and you can put a hologram on the surface of the chocolate because the chocolate is little sugar crystals. And little sugar crystals line up on the surface, and they're small enough grain that they can accept the holograph's record information. So like an old record that had all this stuff just written in these little trails. It's basically the same idea. It's just this just printing the information as little lumps and bumps on the surface. So I don't think that's there's not much to take apart there. It's kind of trivial and silly. The holograms aren't all that visible. Frankly, I don't. Doesn't really appeal to me in any particular way. So I don't think there's anything else to say about it. Yeah, I guess there really isn't. So I'll call that a video then. Oh yeah, I'll fix the thing I broke the other day. In terms of not saying it quite right. So, alright. So we have this concept of the single slit and the double slit. Alright, so the single slit creates a pattern that has a big thing in the middle. So it's two things just kind of blended into each other. And then the rest of the humps are this size. The rest of the little bumps. Alright, and the question is why doesn't that happen, okay, in the double slit? So when you have a double slit, the idea is that, certainly these two surfaces, we know why they're not happening, because these two surfaces are close together. So these two surfaces, this surface and this surface, they're creating the envelope, which is a very wide pattern. Okay, so that pattern obviously has the bigger hump. It's just that it's a really big hump. It's really big. But why don't these two surfaces, okay, they're going to create all these little bars. Okay, why isn't this middle bar extra, a double bar, right? Because it would be doing this and this, these contributions, right? So you have the contribution that goes straight, like you can't see it in this diagram because of the tightness, but you understand that there's a straight line from here that would go to here, so you could understand like this one's combining with the straight line from one surface is combining with the bent line of the other surface and vice versa. And so you have two patterns. You have the one going this way and you have the one going that way in terms of on polarization and off polarization and on polarization and off polarization. So that's what's sort of being created in the single slit, is two are being superimposed on each other in the sense that you have the combination of this, and then you have the combination of this and this. And those are the two on phasers. So the point would be is that this has a phase that it creates because of the length of these lines. And so you could say here's the straight line from this distance. Well, that's not the way to do it. But these distances, all right, so you have a certain distance here that's a certain wavelength. And when you were just using a single slit, right? So when it's an impediment, there's no light going through here. So, it's a little harder to explain, but because you do have the light going through in the single slit. So the point would be is that the phase is because you're combining two sources to make a photon. So there's no light if only one source. If you only got the photons that come through here, you'd have no light. Okay, and if you only got the photons that came through this surface, you'd have no light. And it's only because you're combining two of them that you're reconstructing photons and then getting light. So there's a certain phase for this where the rulers line up. But if I make a new surface over here and add it, this phase isn't necessarily in phase with this. This distance is dependent on this distance. Tells you whether this will be on the notches, the rulers have notches, or whether the notches will be out of alignment. So if the notches are out of alignment, it can't add the photons. So the whole point of the double slit is that you're saying you need a contribution from all four sources. Two sources won't make a photon. You need light from at least three sources or four sources to actually make the little bar show up. So the point would be is the phase created by this, that is the number of wavelength notches inside of this, don't line up necessarily with the notches created by this one. And so they're likely to be out of phase. So the irony would be is this, where the two outside surfaces meet and where the two inside surfaces meet, these two would not be in phase. These sources would not be in phase with this source. So if you get it, these have to be in phase because it's the same light and it's the same distance, the same angle. So those two are in phase. And these two are in phase with each other. But this isn't in phase with this, which means ironically you get zero light in the dead center. And so you see the two lobes. This lobe and this lobe are now visible because you're dead. You got no light in the center. So the two slit pattern, depending on whether you can get this distance to be in phase with this distance, that is, they're precisely just the right nanometers. You know, if you get it. So my prediction is that if you do a two slit experiment carefully, that is, if you could move these surfaces by a few nanometers at a time, there's a point where you actually will get a big center. But there's only one that'll work. Where you get the phase, exactly this phase ends up being the same as this phase. The notches end up being the same number. Obviously this is a lot more notches, but the notch distance is exactly on notch. So it's on phase with this, and therefore you'll get a big center in the two slit experiment. Okay, inside the envelope, of course. But you'll only get it when these distances are precisely, okay, a full wavelength, a multiple of a full wavelength of more distance. But anything that's off by 20 or 30 nanometers, then you're going to see the dark spot in between them, and so you'll see it, it's two lobes. So that's the difference. I don't know, it's a subtle point, but it's sort of important. It's something that needs to be explained because it does seem like, why does this do it and this doesn't do it? And the reason is because these surfaces aren't necessarily a full wavelength different than these two surfaces. That's kind of hard to, even if you do one on purpose, it's hard to do. Because you're talking about a tiny number of, all you need to be is whatever, 4% off in terms of the frequency of the light for the light not to show up, in terms of the phase being off. So there's just not much, you have to get it within 10 or 15 or 20 nanometers worth of accuracy. So anyway, yeah, so I'll throw that in. Anyway, so that was what I was trying to explain yesterday, and I don't know if I did it perfectly this time, but I just mean, it's a subtle point, but it's, like I said, it sort of just says to you, why don't those two outside slits create the same thing you get in the single slit? And the reason is because those photons are only visible when all four surfaces are contributing. Alright, so till the next time and such. Thank you for your attention, I suppose, but I just don't know how much people pay attention because, you know, the comments just sort of indicate a lack of getting it. But we'll see. I think, yeah. I thought there was a dumber one somewhere. Hey, Draft Science, do you know what that? Oh, okay. Thanks for addressing the question. For me, most illuminating point you made was about the words often being used interchangeably. That's probably how I should have phrased the question myself, since that is what seems to get me chasing my own tail most of the time. I didn't realize it was all this. I will try not to be a pain in the ass with kindergarten queries, but the latest question I have about the double slit and the photons breaking, see, this is the part you're not getting, at the edges of the barrier and then recombining at the back surface. Yes, the little bits are scattered. The bullets scatter in different directions, but there's a whole bunch of photons, so there's lots of little bits scattering. So the real clue is the single photon experiments they do. And the real dig is that they really aren't doing single photon experiments. And if they really did the test in the right order. See, this isn't how they, I've said before, but this isn't how they do the experiments, which is just so flawed. You know, the simple way to test whether you have a single photon producing instrument, okay, it's just the simple, obvious thing. Right here you have a source. Just put nothing between you and photographic paper or your sensor. And so you shoot your radiation and you see what your sensor receives when there's nothing in the atmosphere. And you just say, okay, it gets 100 photons a second, some small number. Then you know what you're getting. But what they do instead is they put the experiment in, they put the experiment in the way, and then say, how many photons am I getting? Well, you're only measuring because you're measuring how many survived the process. You're not measuring how many you actually produced. You're only measuring what you got as an outcome. So yes, maybe your outcome seems like, maybe this outcome seems like very few per second. But really, to make that outcome, you had to put in a lot per second. So you didn't do it in the right order. First see what you're getting with nothing in the way, and then say, okay, I have a low source. And they don't do it this way is because if they find a low source, something that seems like very few photons, or like 1 a second, if they could create a gun that made 1 photon a second hit this surface, the fact is as soon as they put this experiment in there, they're going to get no photons. And that's why they don't do it in that order, is because it doesn't work. Because this slit experiment is completely dependent on the fact that you have to have more than 1 photon source. You have to have pieces from a photon there and pieces from a photon over here. So more than 1 photon have to hit this for you to get anything on here. But anyway. Alright, let's see. Kindergarten I have about the double slit and the photons breaking at the edges of the barrier and then recombining at the back surface. Yes. How does that breaking process actually work? It's electrons, for fuck's sake. Sorry. But, I mean, there's no such thing as a surface. There's atoms. The universe doesn't really care about the word surface. It doesn't care about all this crappy, stupid stuff. The universe only works on one principle, okay? Electrons, protons, and electrons. So we know that it's surface. I could say this is a surface. Well, we know it's not a surface. We know what that's really made out of is an electron here, and there's a proton back here somewhere, and there's an electron here, and there's a proton back here, and there might be another electron here, and there might be another electron here, and there might be another electron here, another proton here. We know it's an arrangement of electrons on the surface. And so what is happening is you're putting a photon through this way. So we know that when you put a photon through this way, it gets diffracted and refracted. We know it gets bent a little. I put it in one way, it bends, right? I mean, I guess this would be the better way to illustrate. It goes in this way and it comes out that way. So obviously when I put photons going through past the surface this way, I'm probably going to hit an electron here, I might hit that. And the electron basically moves, okay? And moving an electron essentially recreates a photon, but I don't want to get into all that kind of crap. But the point is that I change the direction of the photon when I move an electron. So when I move an electron, the photon isn't going to go this way anymore, it's going to go some other way. And that's what's creating the phenomenon, is the electrons are bending the photons, so the pieces are being broken off, they're scattering, and as they scatter, going, here's the surfaces, so you could just sort of understand as they scatter, all right, they're getting scattered, they're banging off the other side, hitting the electrons, banging, blah, 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 blah. They scatter off these 2 points, essentially, the little bits. So that's what's coming out in the end, is essentially these 2 point sources are dictating all of these directions, because photons are scattered by electrons. Okay, are you talking about, okay, here we go again, where was I? How does this breaking process actually work? Can a single photon have a wavelength or phase? So again, there's no single photon is already something that has phase built into it. It's quanta at a frequency. To break and then recombine, yes. Or are you talking about groups of photons being knocked out of phase with each other? So this goes back to what I started with the whole video, and the fact that regular physics has completely confused people about what the fuck a photon is, and quanta, and understanding that a photon is a composite object made of nodes. If you want to think of it, like I said, you can apply it to wave theory. So I'm not even arguing that I'm just saying that fundamentally their problem is they broke the corpuscular nature of the universe. But even if they have a wave theory, they should be able to acknowledge that ocean waves come in series of ocean waves, and you could count the waves, and that would be a collection. And a collection of waves is a photon. A photon isn't one single wave in the ocean. That is not a photon. You can't see that. Alright, talking about a group of photons being knocked out of phase with each other. I'm not even 100% sure that I'm using those words correctly. Yeah, well, you can't use them correctly because they haven't given you the vocabulary to use them correctly, because they've given you this stupid notion that wheels is the same as wheel. In this question, I also apologize if it doesn't make any sense. Well, I apologize that physics has, scientists are such shitheads, and they're just not being very logical, or they're not applying the whole point of science is to be technically accurate and to do all these things that are really important, and they clearly aren't being very technical when you're calling a wheel wheels. Very interesting. I'm also wondering why the single slit diffraction. Okay, we already did this, so you're way off the mark. You're not getting this at all with the Huygens crap. I've already debunked Huygens' silly theory. The very idea, again, of something that's dependent, for their theory to work, for it to create these straight line waves, for the waves not to deteriorate by this stupid theory that little tiny waves make the next wave front. The whole thing is silly in the first place, that the wave is made out of a bunch of little tiny things that are making the next wave. But the fact is they have to make it an infinite number, or the wave would start to deteriorate over distance. It would get all lumpy. And so it's a silly concept in the sense there's no infinite number of something in a small space. There's no infinite number of anything in there. It's just stupid. Alright, so I think that's enough now. Yes, so extra bonus material. So, till the next time, and such, and so forth and whatnot.